Good afternoon. Good afternoon. All right. Thank you for coming. We have some very experienced speakers and scientists today to join us, and we're going to talk about managing the facility and how operators can reduce their risk in their operations. Their customers, taking better care of their customers' product while extending float and flywheeling activities, maintaining temperatures and decreasing energy costs. We'll also take a deeper dive into the science behind that, basically the effects of temperature and quality and shelf life of frozen food. On the cold chain across from the farm all the way to the fork, you've heard it before. There are lots of risks that occur, and what we'll talk about are different areas and temperature ranges that can affect food. We'll understand the concept of connecting food with the temperature fluctuations through the cold chain. This also holds true with freezing temperatures as well. So where you have food that's coming in from the field, takes multiple steps, multiple transportation modes. But even when the food is frozen, you have certain risks that are based on temperature fluctuations, based on catastrophes that you may experience, or operational events that occur that you're not prepared for. Customers are requiring more today. From what we understand in the industry is there are tougher requirements on temperature ranges. They require more visibility and verification. Many of you are familiar with some of the certifications that are required depending on the type of production facility you may have, whether you're a warehouser, a distributor, or whether you're just an aggregator. There's many types of heat infiltration. You have heat infiltration that comes from the envelope, from regular operations, from the evaporator fans, from forklifts, humans, lights. Depending on what type of balance you've got to take care of, not only what the heat load of the facility is like, but also what the volume you may have in your facility at any given time. So you have lots of decisions and lots of areas that you have to manage. Part of that balancing act is managing high electricity costs while maintaining that quality and integrity of the food product and keeping stable temperatures, which equate to that quality. So floating for energy savings. There's also a term that the industry uses, which is flywheeling. What are the risks associated with floating? So in frozen food, there's not near as much risks as you would have in medium temperature foods. But depending on that temperature variation and taking into account some of the other variables that you may have to consider, such as how much food you have in your warehouse at a given time, and then the science behind micro-thawing and microcrystallization, depending on the water content of the food, is something we'll ask Denny to elaborate on. So the impacts of the temperature deviations during the storage. We manage the warehouse for frozen foods while controlling energy costs and maintaining food quality while dealing with normal fluctuations, the storage environment, temperature variations, and unanticipated increase in storage temperature due to refrigeration system failure. So as I've mentioned earlier, it may be a catastrophe or it may be an operational event. So at this point, I'd like to hand over to Denny. Denny Heldman is with Ohio State University and is the food scientist for GCCA. Denny, welcome.
Thank you. In the few minutes that we have, I would like to try to deliver and communicate to you some concepts. And it's concepts that have already been alluded to in terms of this, the sensitivity of this interface between a frozen food and its environment. What happens at that interface between the frozen food and the environment is something that probably many of you are dealing with. So yes, we're going to discuss factors influencing air temperature in a frozen food warehouse. We're going to describe the influence of that air temperature on the frozen food temperature. And finally, try to focus most on once that interface is understood and we understand what's happening, what does that do to the quality of that frozen food. And quality here is one of those terms you just have to accept kind of on faith, because ultimately it's whatever the consumer of that product, the consumer that buys that product, prepares that product, and consumes that product, what is their reaction from a quality standpoint? Quality comes in many, many different ways, and I will refer to it in that most general manner. One of the things that I always start a lecture like this with is trying to convey what frozen food quality might mean. And many times we refer to it as shelf life. Shelf life. How long does the quality of that frozen food last? And what is most difficult to accept many times, that even in frozen foods, just like perishable foods, the quality declines with time. There's nothing we can do about that. In this slide, I just suggested, let's say at the time the product's placed in the package, and well, I should say packaged and then frozen, it has 100-day shelf life based upon its quality attributes. That, from that very day that it's frozen, the quality of that food continues to decline. Now, the shape of that curve may not always be linear like I've shown it, but it nevertheless declines, and when time reaches 100 days, 100 days of storage or whatever days of whatever it has taken to distribute that product, the shelf life, that means the quality has now reached a point where it's probably no longer acceptable to the consumer. So that curve, that shelf life is temperature dependent, like shown here. Our standard is 0 degrees Fahrenheit or minus 18 centigrade. The shelf life of frozen foods, ever since I think it was the 1950s or earlier, that has been the standard definition. So when you hear a shelf life quoted, it typically refers to the product being stored at that temperature, how long it will last. However, if the product is held at any time above that temperature, its shelf life declines more rapidly, and it never recovers. So, as an example, I've shown that if a product has a 1-year shelf life at 0 degrees Fahrenheit, if you store it at 4 degrees Fahrenheit, its shelf life decreases to 240 days, just automatically. That much adjustment in shelf life or temperature reduces the shelf life. Even worse, if you store it at 11 Fahrenheit, its shelf life reduces to 112 days. That is documented and research that was done actually in Albany, California in the 1950s. Huge frozen food shelf life studies that were completed at that time. And I don't think we've had anything approaching that since, although there have been various shelf life studies that have helped us, are helping us still understand what these changes are about, what brings them about. Foods, many of you recognize this, contain what happens in a food, no matter what the temperature, its shelf life is based on certain reactions. Those reactions are dependent upon the type of food that we deal with, and I'll have a slide that helps you understand that in a bit as well. So keep in mind, shelf life is not something you can change. It starts when the day the product is frozen. Quality attributes, I've already mentioned, it comes in many ways. Yes, it's the color of that food. It's the flavor of that food. It's the texture of that food. Any and all of those attributes that are ultimately evaluated by the consumer are changing or might be changing depending upon the temperature at which that product is stored. So we're going to talk about the importance of temperature stability. And I think I've already started that by trying to better help you understand what shelf life is. Frozen foods contain small amounts of unfrozen water. Most of you probably cannot appreciate that. I have a slide in a few minutes that says even when a product is reduced to 0 Fahrenheit, it has a small amount of unfrozen water. That unfrozen water is something that changes as the temperature of that frozen food changes. So as soon as you elevate the temperature a bit, that amount of unfrozen water increases. Any increase in temperature results in an increase, just as I said. So think about that. Anytime the product goes through some sort of temperature fluctuation, anytime that it goes through some sort of systematic increase in temperature, a certain amount of water, additional water, changes to liquid from ice. A subsequent decrease in temperature does what? Probably fairly obvious. It refreezes the ice. It refreezes the water back to ice. However, one of the things that we teach right from the beginning in frozen food manufacturing is the more rapid you freeze a product, the smaller the ice crystals that are created in that product. And smaller ice crystals maintain the integrity of the structure. And this is particularly important in fruits and vegetables. So you want small ice crystals. However, in a warehouse, that decrease is slow. And so the ice crystals are larger. And those large ice crystals begin to create disruptions in the structure and typically a loss of quality from a textural standpoint. The best example I always share with my class, think of ice cream. What happens when you take ice cream out of the freezer? It's great the first time. If you leave it out on the counter for what? 10, 15 minutes? You put it back in your freezer. What does it feel like the next time you take it out, and especially at the surface, you have that grit of very large ice crystals. It's the same phenomena that occur anytime there's a fluctuation in a frozen food. So, larger ice crystals we don't want. There's my unfrozen water temperature curve for beef. It drops very rapidly as you go below the freezing temperature, which is just below below 32 Fahrenheit, but it never, ever gets to 0. There's always some unfrozen water in any frozen food. All right, refrigerated space. Just to take a minute or two, the larger the space, the more slowly temperature changes if there's any disruption in your refrigeration. Keep that in mind, and I have a slide that gives you some idea of how sensitive foods are. The middle column is expected shelf life at 0 degrees Fahrenheit. That's the standard, remember? So, yes, seafoods are shorter generally. Fruits and vegetables are longer. A year, ice cream's not bad. However, when you look at the third column, which sort of defines the sensitivity of these products to fluctuations, you'll find that ice cream is very sensitive. So that's the reason you can't leave it out on the counter very long. Some of the other foods, according to that scale, have less sensitivity. So the key thing here, each food has a fingerprint and responds differently to any kind of temperature fluctuation. This is a response of different size spaces to temperature change. So a large warehouse changes the air temperature changes much less rapidly than a large space. This is a study we've done, completed about a year and a half ago. Imagine what happens to an entire pallet of frozen food when it's exposed to an elevated temperature. What this slide shows, and this is what I'll relate to you, the product at the surface is the product that's influenced most significantly because it's the closest to that elevated air temperature. The product that's in the center of that pallet is insulated. Frozen foods are excellent insulators against elevated temperatures. So if you have an entire pallet exposed to an elevated temperature, it's the product at the surface that you must be concerned about. And if you're looking for any kind of indicator of the impact of an elevated temperature, you sample the product at the surface. It's going to be the one that's impacted most. We are now even in a position to evaluate the impact of those kind of fluctuations on product quality. So this happens to be for a specific product because, as I indicated earlier, each one has its own fingerprint. So this would be a picture for a specific product. We could create this kind of picture for any product that you identify, and all we have to know is the composition of it. So, some conclusions. Air temperatures change more slowly in larger volume warehouses. That's the one illustration I provided. Secondly, frozen product temperature deviations decrease with distance from the interface with warm air. That's the pallet picture. So the further away you are from that interface with a higher air temperature, the more insulated the product is against any kind of change. In some frozen foods, temperature deviations impact quality by increasing unfrozen water content, followed by refreezing of larger ice crystals. This is the worst case you can have. And everything we do have to do everything possible to reduce this potential impact. Frozen food sensitivity to temperature deviation values varies with the type of frozen food. This is the fingerprint. Each of the products in that one slide has a different sensitivity to temperature fluctuations. And finally, deviations in air and product temperatures are reduced when a higher percentage of the warehouse space is filled with frozen product or another mass with a similar thermal energy capacity. So the idea is to keep the entire warehouse temperature as constant as possible. This removes any of the sensitivity. It even goes beyond that. During distribution, the product temperature must be protected against deviations from the one that will prolong the shelf life. Thank you very much. I'd be very interested in responding to questions.
Thank you, Dr. Heldman. Excellent. I wish I was that smart. There's a lot of knowledge there. That's a good segue in. It's a frozen product or another mass with similar thermal energy capacity. That's an area that Viking Cold has expertise in, the thermal energy storage. It's an area we've made a lot of progress working with the GCCA. Going to introduce one of our customers, Jason Dreisbach. He's got a facility in Northern California in Richmond. He's completed an installation. We've asked him to join us today and share his experience with what we've been able to do with thermal energy storage. That's forward, that's reverse.
Thanks. My name is Jason Dreisbach. Our family runs about 600,000 square feet of refrigerated and frozen warehouse space in Northern California. I think Denny's done an excellent job of defining why our customers care about temperature stability. Obviously, priority one, as Denny talked about, is protecting our customers' quality. All of our customers are getting more sophisticated in their QC and QA analysis of our 3PL operations. They're wanting visibility into the supply chain They're wanting visibility into the temperatures we're holding products at, and they want visibility across the entire supply chain, both from transportation and warehousing. Obviously, controlling costs is important for any warehouse operator. Let's start with the premise that floating, which is really the time the product is not operating, the refrigeration system is not operating, takes place all the time through all modalities within the system. Whether it's a temp satisfied within a reefer unit or shutting off for a defrost cycle within the refrigeration unit, we all have a certain amount of float within our operations that we're riding a thermal mass on. So for us in Northern California, a lot of our costs of refrigeration are based upon time of day usage, demand charges, and other economic factors that are put upon us by the utilities. What do we do to try and manage those costs? We pre-cool down below the 0 degrees, trying to get to -7, -8, so that we can achieve some period of cutoff to try and defray costs during that period without jeopardizing customers' products. Or should we shorten the floating periods that we allow the product, the warehouse to be on, so that we stay within our customers' parameters. So here's a picture of what the thermal energy storage systems look like in our warehouse. We went through a fairly sophisticated pre-installation evaluation, including the temperature requirements for our customers, facility and equipment that we were running. This facility happens to be on a ammonia refrigeration system. Our utility billing, the time of day usage, our rate structure, how we were currently managing our operations in regards to that rate structure. And we felt that this product was going to help us in our mode to try and control the costs and increase stability within the room. We worked with Viking on the installation process. We had strong communication with them. They were extremely responsive. We even changed things up with a customer change in the middle of the installation process with our racking configuration. They were able to adjust and offer a different configuration for the hangers that would fit our new rack configuration. All in all, it was fairly non-disruptive as any installation can be in an operating warehouse. We worked with them the day before to clear out bays, then we'd be made ready for them to install and have good visibility into what the production cycle is going to be. So the results, I'm happy to say, were really strong. We've extended our float hour from 6 hours to 13 hours. We're only having to refrigerate on the freezer and pre-cool the units during the off-peak, which has dramatically reduced our energy consumptions. Our peak consumption's down 43%. Anybody in California, the PG&E category knows what that means as far as dollar values go. The weekday energy consumption, which are your higher cost consumption periods, were reduced by 20%. And the total freezer consumption was down 35%. Peak demand, which is also a function of how many kilowatt hours are being used at any point in time and is a separate line item charge, was reduced by 29%. And with that, Colin, you've got some representative sampling here of facilities. I know you were looking to try and go over that in more detail.
Yep, thanks.
Happy to answer questions following. Thank you, guys.
Thank you, Jason. The key that we're trying to harp on here is that there is a way to float or flywheel and do it safely, minimize your risk to your operations. And we had some phenomenal results. Jason was the first large facility that we did. We've got many installations in Puerto Rico. We've got installations at many food banks in California. And so we've had different experiences across different facilities. And the larger the facility, typically the more stable environment you'll see. But what we did is we did 2 pre-installation test days and we did 2 post-installation test days. And so if I'll look on here, this orange line here is the average temperature of the highest part in the room and the center of the room, or what we call the racking. And the blue line is post-installation of the average of the top of the room in the center of the racking system. And these, you'd see real little bitty dots. These are hundreds of thousands of data points that we're taking over these periods of time. So as you can see, we started with a 6-hour initial peak period, which was noon to 6 in Jason's territory in PG&E. And where we're starting here starting at this point here is where we align the 2 days before and the 2 days after is the closest point we could align. So the first 6 hours you see very quickly where the top of the room immediately exceeds the upper threshold of the temperatures and continues to rise all the way up to +4 degrees over that 6-hour period and eventually stabilizes out. With all that thermal mass in the room, it will eventually stabilize out, but at a much higher temperature. And as Dr. Heldman was pointing out, once the magic number is 0 degrees Fahrenheit, and once you exceed that, you have a lot more detrimental effect on the product. So the key takeaway here is right off the bat, when the float started, is over 1/3 of the space exceeded the upper limit and was there for the full 13-hour rise. And both the center, you can see in the center of the room where all the thermal mass is, it's pretty stable. But at the height of the room where we have our cells, these phase change material, the cells now, they're doing the majority of absorbing the heat. And they're constantly raining cold down on the product. So it's like having a thermal blanket over the top of your entire facility. And so the key takeaways, we held the temperature below the upper control limit for 15+ hours in this test result. Without TES, 1/3 of the space exceeded the upper limit control right away. And then with TS, all space, so the entire cubic footage under consideration is well within temperature requirements. So that's the kind of key takeaway here is temperature stability is extremely important to the food. Many variables influence the temperature fluctuations. We talked about transportation, we talked about how full the facility may be, what type of heat load you have, any anomalies that may be going on. Temperature fluctuations affect food quality at all temperatures, not only medium temp, but in frozen as well. And the float can be greatly extended with less risk to food in operations with thermal energy storage. The one thing I'd like to bring up is that GCCA has been working over the last 2 years, Stephen. Is that a 2-year project? Coming up with a program, Energy Excellence. They'll be launching it this July. Is that correct? This is an example of just one technology in an entire portfolio of things that you can do as owners and operators to help influence greater quality product, greater temperature stability, a better product for your customer, and give you an edge from a competitive standpoint. Stephen is here with us. He'll be happy to answer questions about the program. And at this point in time, I'd like to open up the floor to questions. So you have Dr. Heldman and Jason here both. Ted?
Colin can probably answer that better. At the time we did it, it was pre them approving it. I know that Colin's been working with them to try and get them approved for the SUP program.
Correct. So the IOUs, the biggest utilities in California, Pacific Gas and Electric, Southern California Edison, San Diego Gas and Electric, we have been approved for what's called an SGIP, a self-generation incentive program. We're also working under custom incentives. So depending on the given application, the utilities have looked at what we're doing, have approved what we're doing, and have supported what we're doing. Okay. We've also, another example in another market in Massachusetts, Eversource had issued a multi-million-dollar grant to install this technology in cold storage facilities, 100% paid for by the utility, simply under a demand reduction program to eliminate demand during their ICAP tag period of the day. So definitely some opportunities out there depending on where you're located. It's a very good question. So as you saw in the picture, the phase change material at the top, they're just cells. I oversimplify it. My engineer hates it when I say this, but think about a gel pack in your lunchbox. So we've commercialized that idea. The formula is designed to specifically go through a phase change at a given temperature. So if you have a freezer that runs between -5 and 0, we've got a formula for that in Jason's facility. If you've got an ice cream product that ranges somewhere between -14 and -20, we have a formulas specific for those target areas. So yes, sir. So we have the formulas are designed, they have a fixed point at melt point, but we ride the longest period of time to leverage that latent heat of fusion. So in simple terms, if that cell is frozen or if it's in liquid state, it's worth about the same thermal capacity as the food itself. It's worth about 0.4 BTUs of energy per pound of mass. When that cell begins to go through a phase change, it increases by 300 times. It goes up to about 135 BTUs per pound of mass. So the time that we've spent in developing our product and our sequencing and the logic in the controls itself tells whether we're going to run a fan, whether we run a compressor, whether we're riding for long periods of time, depending on what we're trying to solve for and what market conditions there may be. And so we have developed a somewhat of a curve. So when you're going through a phase change, it's that formula is the same and constant temperature the entire time. But we've actually got intelligence now that we can tell before it drops off that cliff and goes into a simple state of water. We bring it back in, turn on the refrigeration equipment. All of those considerations are taken into account. We monitor both the air temperature, the cell temperature, as well as a quality simulated temperature. We have a 24/7 portal that customers can access for real-time data. We monitor equipment runtime all the way down to the evaporator fans, compressors, any of the pre-measures of baseline that we've taken prior, and we send our customers a daily report card on how we've performed for every room, for every facility, for every customer.
One of them, for the drive-in bays, it was above, it mounted above on the overhead tie beams. For the double deep configuration, there's a wire mesh deck that was affixed under the top pallet position.
So we've learned over the years there's many different types of racking, so we've been able to accommodate most everything we run into. Sometimes we've even gone to a ceiling installation in certain circumstances. Question, we've had multiple installations where we had to meet fire code requirements. As long as we maintain 50% space between the cells, we've met all fire code requirements. In small applications, we actually have a solution for freezers as small as a walk-in freezer. And we have a type of installation method that we work around lights in those rooms, the sprinkler heads, plumbing, I-beams. So we've learned some lessons and what I like to say built some character over the years developing the solution. That's what we prefer to do. If there's an existing system, we'll simply act as a sub. Just plug it in. We send suggestions through backnet communication. In many cases, if the system has the capacity to allow us to put our sequence or our code on their system, we prefer to do that as well, as long as the customer has eyes on the facility in a monitoring system. So we're flexible in working with the customer. So the question was, do we have any experience interfacing with a solar installation? Is that somebody? Yes, one of our installations is the San Diego Food Bank. It was actually an installation where that was part of an emerging technology study that was sponsored by the California Energy Commission. Small facility, they roughly about 5,000 square feet, but they already had a solar installation on their roof, had a small amount of excess that they were selling back to the grid at a discount. Our goal was to keep their load off of the grid during what's called the duck curve period of time. Many of you may understand what that is, but at the end of the day, when the sun goes down in California, there's so much solar that a lot of that commercial load comes back on the grid very quickly, so it shoots up. And it's very difficult for the utilities to manage and the ISO to manage. So the hopes for the test that we could stay off for about a 4-hour window to help them prove that we could keep that load off. We actually perform 12 hours from sundown to sunup. We ride 12 hours every day. We drop from about 40 kW down to less than 1 for a 12-hour period. So it's a very good match with solar. It depends on how much solar there is at a given facility, if there's excess. But definitely it is a solar storage technology where we can store in the form of cold. So we run that refrigeration equipment at maximum capacity. We freeze our cells, we put all the energy stored in that fashion, and we're able to ride long periods of time and maintain the quality of the food and the temperature. Everything that is in the phase change material, different types of salts and water, they're all a water-based type of solution. So it's basically the same type of ingredients you would find in any food. Okay, I think we're on time.
You're ahead.
Okay, excellent. Well, thank you very much. We appreciate your attending.